In this video, we're gonna go through an example of applying an expectation maximization algorithm to a particular problem. So, let's say that you have a data set of the following histogram. So you have discrete data which can take only three values, 1, 2, or 3, and you have like approximately 30% of ones, 20% of threes, of twos, and like 50% of threes. And you want to fit some distribution into this data. Well, obviously, if you want to fit any distribution, you can just use this histogram as the best fit. But since we want to see how EM algorithm applies to these kind of problems, let's say that we know that this data came from a mixture, and we want to find the parameters of this mixture. So let's say that this actual data was generated from the following data, from the following mixture. So the probability of xi is equals to a mixture of two distributions, alpha times p1 plus 1 minus alpha plus times p2. So p1 and p2 are our probability distributions, and alpha and 1 minus alpha are the weights, and alpha is a parameter. And here I will not write conditioning on the parameters alpha and gamma and etc. anywhere, just for simplicity and to write a little bit fewer symbols. But the conditioning on the parameters is everywhere. And let's say that the mixture components, P1 and P2, looks as follows. So we have P1, which equals to 1, 2, and 3 with probabilities alpha, 1 minus alpha, and 0. Why? Well, because if we use some distribution which can take any of these three numbers with any probability, then we can just use this histogram as the best fit for P1 and just forget about P2. So let's forbid P1 and P2 to take some of the values, so they have to cooperate to explain this data well. Let's say that P2 has one parameter, beta, and it takes values 2 and 3 with some probabilities which we don't know. And let's try to estimate this alpha, beta, and gamma by using the expectation maximization algorithm. So, for expectation maximization algorithm, we need two things. First of all, we need initialization of our parameters. And let's say that we initialized them to be alpha 0 equals to beta 0 equals to gamma 0 equals to 0.5. Just for concreteness. And also we need to define the latent variable model, because expectation maximization is something that works good for that was invented for latent variable models. So let's say that we introduce a latent variable ti for each data point xi, which will say from which of these two components xi came from. So we'll have a picture like this. Xi is caused by Ti. And Ti can take two values, 1 or 2, with some probabilities. So this way, the probability, the prior probability of Ti being 1, for example, is just gamma. So it's the weight of the first component of the mixture. And the probability of Ti being 2 is just 1 minus gamma. And you can easily define the conditional probabilities. So probability of xi, given that, for example, Ti equals 2, is just the second, the probability according to the second component of the mixture. So it's P2 of xi. So now we have everything defined, and we can use the expectation maximization algorithm to find the best values of parameters alpha, beta, and gamma we can we can find it with this kind of algorithms. So let's start with the E step, or expectation step. On the E step, we want to find the posterior distribution on the latent variable ti. So we want to find Q of ti, which equals to the posterior distribution, P of ti, given Q of ti equals to C, for example, and we can put C here, given the data point xi, and the parameters, but I will omit them as usually in this video. So let's see how can we do it. Let's start with probability of ti equals to 1 if we know that xi equals to 1. So we can find this expression by using the Bayes rule. This thing equals to the following ratio. So it's proportional to the joint likelihood, the joint distribution, P of ti and xi, which equals to the P of xi equals 1 given ti equals 1, times the prior distribution P of ti equals 1, divided by the same thing, but for ti equals 1 and ti equals 2. So sum with respect to all the values of the latent variable. Probability of xi equals 1 given ti equals 1. So the same thing as in the numerator, times the prior, plus the same thing but for ti equals 2. So P of xi equals 1 given ti equals 2, times the prior, P of ti equals 2. And we can compute this thing for our model. And so we know our current values of parameters alpha, beta, and gamma. So this prior is just, this conditional distribution is just P1 of xi equals 1, so it's alpha, times the prior, which is gamma, the prior probability for ti equals 1, divided by the same thing, alpha times gamma, plus probability that this particular point came from the second component of the mixture, which is 0, because the second component of the mixture never generates us ones, times its prior probability 1 minus gamma, which is just 1. And this totally makes sense, right? Since we know that the second component of the mixture can never generate you number 1, it just means that if we see number 1 in the dataset, it was certainly generated by ti equals 1, so by the first component. And we compute the same thing. We can compute the same thing for other values of ti and xi. So P of, for example, ti equals 1 given xi equals 2 will be, using the same reasoning, the conditional distribution, which is alpha 1 minus alpha, times the prior distribution, which is gamma, divided by the same thing, 1 minus alpha times gamma, plus the same thing, assuming that this data point came from the second component of the mixture, so 1 minus beta, times 1 minus gamma. So the prior distribution for the second component of the mixture. And this thing, if you substitute here the numbers from our initialization, it will be just 0.5 times 0.5 divided by 0.5 times 0.5 plus the same thing. Because of our particular values for the initialization. And this is just 0.5 in total. So we found our posterior distribution on ti given xi, and we can do the same thing for other values of ti and xi. This way we can compute the E step of the expectation maximization algorithm for this particular model. So in the next video we will discuss the M step, so how to update the values of parameters by using this computed conditional distributions on the latent variable.